Okay, so the last few sections are all kind of very similar to each other again. So 3.2 is framed in terms of distributing questions or distributing presents, but basically it's if I have n objects and I have to give n1 to the first person n2 to the second, blah, 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 nk to the kth. How many ways can I do that? And so I have object 1, object 2, object 3, object 4, blah, blah, blah. And then n1, this guy is getting n of them, or n one of them. So, and I don't actually care about the order that I give it to him. So I can think of this as I'm putting an order on this whole set. I'm putting an order on these n things. So that's n factorial. And then n1 is getting my first person is getting the first n1 of them. But he doesn't actually care about what order he gets them in. If he opens his first present first, or the second present first, or the third present first, it doesn't matter to him. So divide by n1 factorial, because the order doesn't matter and there's n1 factorial ways to put the order on this. So basically, I'm looking at this whole list, but I don't care. I care what elements, what objects are in my first n1, but I don't actually care about the order within that. So I can divide by n1 factorial there. Same thing here. There's n2 objects going to my second person, but he doesn't care about what order he gets them in. So divide by n2 factorial. I care about what's in between n1 plus 1 and n1 plus 2, what elements are in that list, but I don't care about what order they appear. And the same thing with n3 all the way up to nk factorial. So this right here is how I'm going to do this. That's how many different ways I can distribute presents, as the textbook frames it, to k people who are getting not necessarily the same amount of presents, who are getting n1, n2 through nk presents, respectively. So that's this guy. And this is actually, it's surprisingly closely related to the second question, or it's not that surprising. It's pretty easy to see the connection once you stop and think about it for a minute, of how many different ways there are to rearrange a word. So you might think if the word is n letters long, like many, then it would be n factorial. So 4 factorial, or 3 factorial for how. In the case of how, we would get how, we would get whoa, we would get HWO, we would get who, and then we would get how and oh. So in this case, yeah, actually it is just n factorial, it's 3 factorial. It would be the same thing for many, but if I wanted to do rearrange, actually it's not, because I don't care if the permutation that you give me is the first R, the second R, or the third R, or the first E, or the last E, or the first A, or the last A. So if it's rearrange, then this is basically the same question of that I'm working with up here, except I'm not putting, I'm assigning spots to letters to my kth letter, or to my first letter, to my second letter, to my kth letter, instead of assigning presents to people or objects to people. So if I want to do rearrange, A, E, G, N, R, is the same if I'd, regardless of what order, whether this R is the first R or if it's the third R, right here. So what it's going to be. So it's n factorial ways that I can order these guys if I actually cared about what it was. But then I have to divide by the cardinality of A factorial. So that's just 2 factorial. The cardinality of E factorial. That's just 2 factorial again. Cardinality of G factorial. That's just 1. Cardinality of N factorial. Again, just 1. And then the cardinality of R factorial, which is 3 in this case. There's 6 because it's factorial, but 3 factorial. So if I want to look at how many anagrams, I think I'm spelling that correctly, for a word, are there for a word? The answer is n factorial, where n is the length of the word, divide by n1 factorial, so that's how many times the first letter appears, times however many times the second letter appears, where not redundant. So R is just the first letter here, it's not the first, the fourth, and the fifth. And 3 factorial all the way up to my kth letter factorial. So to give you guys what's happening? Pause. Okay. So if I want to reorder the word tat, T-A-T, then I would have a few options. I can put T-A-T-T, I can do the original one of T-A-T, or I can do T-T-A. But that's all I get. Anything else is just going to be identical. So that's going to be, so that's 3 factorial divided by 2 factorial times 1 factorial. So that's going to be equal to 6 divided by 2, and that's equal to 3, which checks out. What about letter? L-E-T-T-E-R. Well, if I were to list out all of my options, it would take me a while, but I can also just plug it into this formula here. And so this is 6 letters long, 6 factorial, and then we would get L only appears once, so that's 1 factorial. E appears twice, so that's 2 factorial. T appears twice, that's 2 factorial. And R appears once, so that's 1 factorial. So we get 6 factorial divided by 2 factorial. 2 factorial is equal to, what, 6 factorial is 720, I believe, divided by 4. So that would be 2, so 720 is 3 times 24, that's 180. 180. We should have 180 options for ways to rearrange this. So like I said, that would take a while to write everything out. But we've got this nice little formula to tell us how many different ways there are to do it. Okay, so now the last related question that we're going to ask is, if I have n identical objects, your textbook describes these guys as pennies, so you don't really care which penny you get. They're all minted the same year. None of them's a special mint condition penny printed in 1905 or something. So we have n identical objects that we want to distribute. Distribute between k people. How many ways can I do that? And it's a bit surprising that we get this formula, but it's actually n minus 1 choose k minus 1. And the reason that we get this is because we can line up our objects 2, 3, 4, all the way up to n. And our first guy has to hit here. He has to be there. But he has to have at least one. He doesn't have to stop at one, but he has to have at least one. But we don't have to stop at that. We can keep going, and we can have him go over. We have to pick a point for him to stop. Let's say we pick it at 3. Then the next guy picks up here, and then we have to pick another point for him to stop. And then the next guy, and then we have to pick another point for him to stop. And it turns out we're actually picking k minus 1 of the places for him to stop. And he can stop at any point other than n. He can't stop at n because that would mean that the last guy doesn't get any pennies. And we said that everyone has to get at least 1 penny between k people. Sorry, I didn't specify that, such that each person gets at least 1 penny, at least 1 object. So this first person has to start off at 1 and then stop at some point. The next person picks up at the next point and then keeps going and keeps going. But nobody can, the last person can't go all the way, or can't go, the second to last person can't go all the way up to n. So that means that there are n minus 1 possible stopping points for k minus 1 stops. So the ways that we can distribute this are n minus 1 choose k minus 1.